Well, good evening, colleagues, friends from near and far. I'm Professor Sean Weinkart. I'm the head of the physics department, and it's actually very good to see a few familiar faces that I haven't seen for some time. So firstly, a warm welcome to all of you. And I think this opportunity presented to us by the South African Gravity Society creates an opportunity for us to really share and also bring the best that is available in terms of the research experience and expertise that's available in this field to study something that I think has been, one of the things that we've engaged with as human beings from, I guess, from birth, fighting against the force of gravity. And today, in fact, we are brought together, gravitated to this very small piece of speck of dust in the universe to share with each other and with our colleagues new developments in our understanding of gravity. What is also amazing is that we have experts locally from South Africa, various institutions, UKZN, Stellenbosch, Wits, etc. But we also have special guests who are presenting talks at this particular conference from the Netherlands. Dr. Heino Falter, warm word of welcome to you. Yen Keng Lim, all the way from Malaysia. We have William Kinney from the United States. I think he's probably still getting used to the time zones. And then Martin Bucher, who's from the University of Paris, but he also has a foot here at Stellenbosch and UKZN. So I'm not sure if Martin is around, but he's probably going to be in the vicinity of Stellenbosch. So one wonderful thing about conferences is that it brings people together, as I've mentioned. It creates the opportunity for us to really share or have a conversation around various topics. In this case, we have a topic that is very specific to this particular field, which deals with gravity, but it also allows us a bit of insight into the bigger world, the cosmos. And for that, I think we are very fortunate to have one of our local experts, Roger Deane from the University of Witwatersrand, and I think you also share a position at the University of Pretoria, so all the way from Gauteng, to come and share with us a bit of news. So without further ado, I'd like you to tune in to the Cosmic Symphony, where we will glance into the larger universe through these gigantic radio telescopes. And I think for the younger audience here, I don't see many learners. I think there are amazing opportunities for you guys to explore. And we have the experts right here in Stellenbosch, so please make use of this opportunity. Ask those questions that you've had for many years. Bug them, ask those questions. So without further ado, I'd like to pass the stage on to the organizer of the South African Gravity Society's conference here at Stellenbosch, Dr. Ansel and John. Thank you very much.
Good evening and welcome to Stellenbosch. This week marks the first time that we are hosting the South African Gravity Society Conference. This conference has a long history and began as the South African Relativity Society in the 1990s. One of the aims of the society is to provide a forum to disseminate research in the field of general relativity within South Africa. Tonight, I'm pleased to announce another milestone. The first public talk associated with the SAGS conference. An event like this would not be possible without the hard work of my fellow conference organizers in the physics department and the generous sponsorship of the National Institute for Theoretical and Computational Sciences, the Center of Excellence for Mathematical and Statistical Sciences, as well as the Faculty of Science here at Stellenbosch University. Nature has four fundamental forces. These forces are successfully modeled by quantum theory, which governs the electromagnetic, weak and strong nuclear forces, and general relativity, which governs gravity. General relativity was revealed by Albert Einstein in 1915 and profoundly altered our understanding of time, space, matter, and energy, particularly the interplay between them. To quote the American physicist John Wheeler, matter tells space-time how to curve, and space-time tells matter how to move. The past decade has borne witness to some of the most remarkable verifications of general relativity, such as the discovery of gravitational waves by LIGO and the discovery of black holes, which were directly imaged by the Event Horizon Telescope. The era of gravitational wave astronomy has truly begun. And this brings me to tonight's speaker. Roger Deane is a professor at the University of Witwatersrand in Johannesburg and an extraordinary professor at the University of Pretoria. He completed his doctorate in 2012 at the University of Oxford and returned home to carry out postdoctoral research at Rhodes University, as well as the University of Cape Town. In 2018, he moved to the University of Pretoria, where he established the Radio Astronomy Research Group. He now holds the DSI NRF SKA chair in radio astronomy at the University of the Witwatersrand, where he serves as director of the Wits Center for Astrophysics. His research interests are focused on the cosmic evolution of galaxies and their supermassive black holes, using the power of next-generation radio telescopes, such as South Africa's MeerKAT radio telescope, a precursor to the Square Kilometre Array, and very long baseline interferometers, like the Event Horizon Telescope. He is also the 2023 NSTF South 32 winner of the Science Communication Award. Please welcome Professor Roger Deane, who will talk to us about tuning in to cosmic symphonies with giant radio telescopes.
Thanks, Well, good evening, and thank you for that very, very kind and warm welcome. It's great to be here, hosted by the South African Gravity Society in an important conference this week, and will later serve as host to George Ellis's 85th birthday. Then by Stellenbosch University, thank you, and by NITheCS. I'm very, very pleased to be here. It's great to see some youngsters in the audience in their pajamas. Fantastic, highly encouraged. Please enjoy yourselves. We've just had an incredible 2 weeks in Cape Town in the triennial International Astronomical Union General Assembly, the first one in Africa. And I think, you know, when people look back at this 2 weeks that we've just had, it will be recorded as, you know, a milestone in astronomy on the continent. And really, it was quite something to look back at how far African astronomers have come and to look at the very exciting things on the horizon. Tonight, I want to talk about two giant radio telescopes that will be on the African soil, partly at least. MeerKAT, which will become the Square Kilometre Array, mid-frequency array on the left there, and the Event Horizon Telescope, which will be expanded to Namibia, and then hopefully a few other African countries to make movies of that black hole in the center of the Milky Way that you see on the right. And I really think that these two telescopes will be recorded as marking, you know, really doing transformational things in astronomy in more ways than one. I have no musical talent whatsoever, but this talk does have four movements. I'll start by giving you a bit of a cosmic inventory so we can make sure we're talking about, aware of the relevant ingredients. I'll then move on to these two giant radio telescopes. I'll focus in a little bit on our Milky Way's black hole, which is interesting for a whole host of reasons, apart from being in our home galaxy. And then close with looking beyond to the millions and billions of black holes across cosmic time and how the Square Kilometre Array will survey those. So beginning with the cosmic inventory, this is a view from the bushveld of the southern sky, highly recommended in combination. You can include a campfire, perhaps a glass of red wine, but a beautiful scene that I hope that you've all enjoyed, and those visiting us for the first time will enjoy during their stay here. Now, of course, the view of that was improved dramatically by a telescope. And Galileo Galilei, he did not invent the telescope. That was invented, as I'm sure our Dutch colleague, Prof. Falco, will remind us, years before in the Netherlands. But he was the first to use it to do a scientific study. And wow, did he unveil a number of things. And really our drive to build new telescopes is to explore the universe in greater depth, as he did for that first time, discovering those four what are now referred to as Galilean moons around Jupiter. And of course, he was the first to see the craters of the moon. He was first to see the phases of Venus, changing our cosmological volume. New telescopes bring enormous new insights near and far. Of course, we've now been able to go beyond Jupiter, behind Saturn. This is an amazing image from Cassini, showing the rings backlit by our sun, and the Earth and the moon as a single pixel, the opposite to what I like to show the sun that we orbit as a movie, reminding us of the fact that we live in a very dynamic universe. But that sun created, like all other stars, in some stellar nursery, and we see these beautiful images from the James Webb telescope of these stellar nurseries, forming new stars, and it never hurts to remind ourselves how, that's a pity. Not only are you seeing gravitational waves, but it's too much, it seems, to stream. But the billions upon billions of stars in our own galaxy, and what you're looking at there are effectively every pinpoint is a star. And if we, on top of that, think of how balance of probability, there's a rocky world orbiting around every single one of those stars, isn't it remarkable to think that, we probably aren't alone? But here's the best model of our own Milky Way, our home. There's a bar in the center there, these beautiful spiral arms, and you see that if you think of a flattened egg, when you sit in the bushveld and you look up, you see that disk around you. And that Milky Way galaxy is pretty average. I mean, statistically, that's what you'd expect. If you look at the extragalactic radio sky, like I do, you see billions upon billions of galaxies in the deepest images. And that Milky Way galaxy is just one average galaxy, one little smudge in that huge image, covering many, many millions upon galaxies. And if you pick one of those smudges, they range from near and far. There are a handful of stars here that are in our actual galaxy. So there's one, there's another, there's another. These sit in the foreground, very nearby. And the majority of these are these smudges that are slightly reddened, slightly blue in some cases, and some of them on the other side of the universe. So 13.3 billion years away for this little smudge that you see here. That's right, 13.3 billion years away. What does that mean? So essentially, our telescopes have become so powerful since the time of Galileo that they've become time machines. When we peer at the end of the universe, you're seeing on the left-hand side here, the Big Bang. And moving along here is cosmic time. And as that process unfolds, the universe cools, the first galaxies form, stars and black holes form, galaxies form. And when we peer back in time, when we look at these deep images that I've shown, we're actually peering back in time. Now, to illustrate the speed of time, here's a ping pong match between the moon and the Earth. And that's the length of time that it takes for a photon to bounce back and forth. Now imagine 13.8 billion years of a photon traveling. This is why our telescopes are cosmic time machines. Now, included in those little smudges, some subset of them, well, certainly all of them have, at least the most massive ones, a supermassive black hole at their center. And some of those are actually accreting, actively feeding on matter. And some of them spew out jets, but they shine very brightly because the gas that they accrete gets very hot as it loses gravitational energy and falls onto potential energy and falls onto that central supermassive black hole. Now, so included in this image is not only smudges of tens of billions of stars, just like our Milky Way, but at the heart of that, for many of them, is a supermassive black hole that can range anything from 100,000 times to 10 billion times the mass of our sun, squeezed into something tiny. So really, there's this cosmic tapestry, there's this evolution of much more than individual island universes when you look at a galaxy like our Milky Way. But in fact, there's this giant cosmic tapestry, and you can see it evolve here. What you're seeing is the galaxy evolve in time. You're seeing filamentary structure, sponge-like structure, or neural-like structure emerge. And at the most dense points that are colored to reveal the density, you're seeing material fall in and form stars, the most massive of galaxies, at those interconnections of these filamentary structures. And over time, the black holes at the center of these galaxies accrete so much matter, they start to have an impact on the environment. They actually start to eject stars, gas, out of the inner vicinity of their galaxies. As they do that, they actually have an impact on the environment, and they shape their environment. So the galaxy, the universe is this, not only this cosmic tapestry and dark matter structure that these galaxies form on, but there's active feedback of the black holes and the star formation that's going on in this. Right, so the second movement is going into talking about these giant radio telescopes. And when I say radio, what do I mean? Well, it turns out you can observe the universe across the electromagnetic spectrum. For many, since the time of Galileo, and for tens of thousands of years, we've looked at the universe just using our eyes. But that was just an evolutionary advantage. Using our eyes adapted to use the photons that were most abundant, bouncing around thanks to the rough temperature of our star being at about 5,000 Kelvin, 5,000 degrees centigrade. We can do astronomy across the electromagnetic spectrum that ranges from gamma rays, X-rays that have a look at your bones, ultraviolet that gives you sunburn, our favorite visible. The kids really love this one, night vision, through to microwave that literally heats up your food. Well, not quite, but microwaves, and then through to radio. And as you go through that range, the wavelengths go from being very, very short, sort of atomic, close to atomic size, and then all the range down here, where our MeerKAT telescope and a telescope like that observes wavelengths of light that are roughly this size. So a huge, huge range. What you can see here is that some of these have to be in space. They have to be above the atmosphere because the light that they're observing cannot penetrate through the atmosphere. So for example, X-rays, you wouldn't be able to put an X-ray telescope on the Earth. You have to put it in orbit. But we're quite fortunate, optical and near infrared and radio waves, we can put these on the Earth, on the surface of the Earth. And that's really handy in radio because these wavelengths are so long, you really want to build big ones and spread the antennas out very far. But I'll come back to that in a moment. Right now, I want to contrast the radio with the optical sky. We're not going to do the whole electromagnetic spectrum, but this is an image that you would be familiar with. You're seeing stars, you're seeing some galaxies, and this is a very, very massive galaxy in our local universe. This is part of the Fornax cluster. Now, that's looking at it through wavelengths that our eyes are sensitive to. We're basically seeing stars, maybe a tiny bit of dust, but these tend to be devoid of dust, mostly just stars in the center of the smudge, and it peaks towards the center there. But if you put your radio eyes on, you see something completely different, far less prosaic. In the inner part there, this is the same scale, you're seeing a supermassive black hole eject 2 jets. There's a whole lot of relativistic electrons that are accelerated from the immediate vicinity of that black hole to a scale that is far larger than it, far larger than it. And this is essentially plasma electrons spiraling in magnetic fields that are obviously unseen to us, but this starts to light up with something called synchrotron radiation. And we see a completely different picture of what's going on in and around us. Notice how that's far beyond the extent of the stars. And the radio gives a completely different perspective on the physics that's at play, both in the galaxy and beyond the galaxy. Using as many as many telescopes across the electromagnetic spectrum is the key to get the most holistic picture. So South Africa is focusing on MeerKAT at present, which is a radio telescope in the heart of the Karoo. This is a photograph I took with my phone on the inauguration day, which seemed to come out fairly well. And what you've got is a cluster of antennas. This is about 1 kilometer across, and they spread out to about 8 kilometers, the maximum distance between them. And if you look in the center there, they're very clustered, and that's for a very specific design reason that I can go into a little bit later. But each of these is big, 13.5 meters. There's 64 of them. And they observe, as I say, light that's on average about about half the width, half the length of this ruler. And the sharpness of the image at that wavelength, if you look at the full moon, you will see if you take about 100th of that, that's about the sharpness of the image, which is going to improve by about an order of magnitude when we have the Square Kilometre Array. So I'm sure you've seen in the press that, MeerKAT and radio telescopes, they're these big data machines. Why is that? Surely if you're taking photographs, why does this data explode? And I want you to think about this in terms of handshakes between different people in this room. So if you think of the telescope, don't think of the individual antennas, think of the connections between as a network. And think of each of these as an individual handshake. So if we all stood up here and shook each other's hands, that's a lot of handshakes. It'll take us a long time to get dinner afterwards. That's what an interferometer is doing. These signals are picking up a specific spatial tone, if you will. They make one measurement. There is an handshake which compares the voltage that's sensed above one antenna with the other effectively. And it does so every unit time, where unit time can be milliseconds, it can be shorter even. And it does so for many, many frequency channels, many, many tones, and it does so for 4 polarizations at the same time. So this blows up because every unit time and every unit frequency, for MeerKAT, you've got about 2,000 handshakes going on instantly. We're going to be upgrading, MeerKAT will be upgraded to MeerKAT Plus, and that'll go to about 3,500 antennas if another 20 antennas are added. And then eventually SKA Mid with 197 dishes goes to almost 20,000 of these, happening on millisecond timescales for, as you'll see in a moment, many, many different frequency channels. So just very briefly, for those that are in the department and a bit more familiar with Fourier analysis, where you decompose an image into multiple spatial frequencies, here is a building at the University of Victoria that has some periodic structure, both in this direction and in this direction. It's difficult to see with this resolution, but you can see some power off-axis here, which is to say it's picking up periodic structure. There's also this big period which it sees, and that's that vertical line. Well, it's breaking up the image into, if you compare it to a symphony, you're breaking it up into the different tones. It's a way of, I think the best expression I've heard is that, if this image is a smoothie, the Fourier transform, have I really messed this up? if the image is a smoothie, if you could do the reverse of the blender, I've completely, that was my go-to expression. I've gone blank for a second, sorry. So the critical component here is that you're missing information. You're missing information, you have to make do with what you get. It's like, you know, if you want to make a telescope the size of the Earth, you build a mirror the size of the Earth, but you can't do that. So you have little shards of glass at strategic locations. And so here, we only sample small sections, or if your hearing could only hear part of the symphony, and you try and recreate. So you make a lesser image, but you do what you can. So it's a bit like if I have to compare it to sheet music, you know, some of this is in focus, some of it is blurry, it's imperfect, what you recreate. Maybe you can't quite see the lines here, but this is what we do with the radio interferometer. We try and disentangle the different ingredients of the smoothie and recreate the image as best as we can in order to do the physics with the image. Now, another thing we can do is we can see colors in radio. It might sound strange, but we can see color. The only reason we see color with our eyes is because of a different intensity at different wavelengths of light. So with radio, you can do the same. So this famous image of an interacting galaxy pair, if you split it up into 3 filters, R, G, B, you can see slight differences here. The very massive star formation tends to be bluer because the hotter stars burn bright at higher temperatures, so they peak at a higher temperature. Whereas cooler regions will be redder. This will be less obscured by dust for reasons I won't go into, but you do see differences there. Now with radio, because we've got these long photons that have a much longer path length, we can sample these and we can split it up into, it's much easier to split this up into many, many more frequencies. And so for MeerKAT, we split it up into 32,000 channels. Now, the data challenge is therefore that coupling of many, many handshakes in the room at every moment, as well as these many, many different frequency channels. When you combine that, you get to extraordinary data rates that we have to keep up with. So the current MeerKAT archive, if you do a typical observation, you get about a terabyte per hour. Terabyte per hour. What is that? Probably on average these days, it's probably about 20 movies per hour at high resolution. So this is a major challenge. And you can see that the archives that we will require with the SKA are comparable to the big tech companies. So is it worth it? Why do we do that? Is it just to sound cool in talks, or what's the point? The payback is if you make many, many samples, you recreate the symphonies as best as possible. You make beautiful images of the universe, like this one of the center of our galaxy that was released on Inauguration Day, the MeerKAT Inauguration Day, which it just, I mean, not only was it the first major science image released by a new interferometer, which is a very difficult thing to build, but it was just so far advanced on what had been built. And part of that reason is because the Milky Way passes right above us. We've got a fantastic view of it. But the dominant factor was this amazing radio telescope. So if you, again, use the moon for scale, this part of the sky, if you had radio eyes, would be roughly that scale. So it's about half a degree across. And at the heart of that, which I'll come to, lies a supermassive black hole, about 4 million times the mass of the sun within a region of the orbit of Mercury. Right, so we're going to be talking about black holes, black hole shadows, and when black holes come in pairs. Now we had a great introduction to black hole shadows this morning from Heiner Felker, but as he discussed, there are really 2 key concepts here to understand that shadow, that ring-like feature. One is light bending around the black hole, and the other is light actually being captured by the black hole. And this animation expresses it well. You can see photons that are buzzing around in the vicinity of the black hole, bad lag again. And you see that some of the photons actually start to orbit. Some are deflected, some orbit, and some of them are captured and blocked by the black hole. And the end result of that, if you look at from a distant observer, is to see a ring-like structure, and general relativistic magnetohydrodynamical simulations predict this feature. And in 2019, the Event Horizon Telescope collaboration released that first image of a black hole, M87 star. An extraordinary achievement, a discrete objective to spatially resolve the first black hole, and an incredible achievement. It's only possible with this giant radio telescope, which is spread across the Earth. It's put as far as possible, you put antennas as far as possible, or shards of glass as far as possible apart. The reason you do that is the further they are apart, the sharper the image that you see. You would ideally want to make this entire thing a mirror, but you can't. It's a little expensive and tough to justify. But you can put strategic shards of glass all over the planet and use that trickery with smoothies and blenders, if I can ever remember it, and recreate the image, recreate the symphony to make this image. Now, ideally, you'd put these in space, but as you might see here, these are some heavy dishes, hundreds of thousands of tons collectively. So to put them in orbit would be really tough. So they're in as close as they're in locations that are as close to space as we can kind of economically get. This is at the South Pole Telescope. This is the Atacama. You can see volcanoes in the distance, and this is in Hawaii, on top of a 4,500 meter volcano. So I've introduced two telescopes. I've introduced black hole shadows and black holes. Let's move on to our Milky Way black hole, which you just saw an image of. Yeah. Now, if you look at the beautiful Milky Way sky from here in the southern hemisphere, you turn on, that's not quite to scale, but if you turn on your radio eyes, that's where that sits, right in that sort of brightest part. It's quite dust obscured, but you'll easily identify with an app. So encourage you to look at this image, look there, because as you saw in this previous image, that's the scale of the moon relative to that. And imagine being able to see with radio eyes, particularly the youngsters. Now, the image I showed you, the black hole shadow, and the first image that was released of M87 star. This is a really massive black hole, around 6 billion times the mass of the sun. So the shadow feature is roughly our solar system sized, whereas the black hole at the center of our galaxy is about 4 million times the mass of the sun, about 1,000 times less massive, but it's also 1,000 times closer. So by chance, appears to be roughly the same scale, but that would fit inside of Mercury's orbit. Now that's crucial because that means that the dynamical timescale, the timescale which it takes stuff to orbit around this black hole, is way faster than it is for this one. All right, it's sort of minutes instead of months, and that's an important. That's a huge challenge technically. I mean, think of trying to take a long exposure photograph of some 3-year-olds running around. It's tough, but it's a huge opportunity in order that can test gravity in some pretty fundamental ways. So this is a key reason why this is the Earth viewed from that black hole. Now, if you think about where you put your shards of glass, you really want them facing up to the black hole in order to make the best possible reconstruction of it. So here we have, this just demonstrates the power Africa has, geographic strategic advantage it has in contributing towards movies of that black hole, the center of our Milky Way. There's only one. We've checked. There's only one. It's our best opportunity to make dynamical movies of black hole, and we happen to be in the southern hemisphere with it flying, traveling right above every day. So we have a unique opportunity here, and in synergy with the Africa Millimeter Telescope sitting in, which will be in Namibia. That is a powerful synergy together with our European partners. You can see this is the Square Kilometre Array of the millimeter telescopes, ALMA. We partner with the South Pole Telescope and with Central America. So we really are extremely well located to contribute towards the Global Event Horizon Telescope. So we're exploring a few sites, seeing and doing some initial costing. There are, I'm sure many of you know SALT. So it turns out with some new technology, Sutherland may be a high enough site. There's Ben McDewey in the Eastern Cape on the border with Lesotho at 3,000 meters. We're exploring, and we've got some equipment up there doing some testing right now to see, to look at the quality of these sites to see if it's close enough to space or not. And you can see here the sort of roughly 1,000-kilometer baseline with our Namibian colleagues, which turns out to be very important for all sorts of reasons, both scientific and technical. So, if we look towards the future, there's this iconic image. This was after inauguration. Ian Hayward from Oxford reprocessed some data, made a larger map, and changed his color scale for the re-release. But this beautiful image of the center of our galaxy, which frankly I believe belongs in a modern art museum. I'm slightly biased though, so I accept that. But what Michael Johnson from Harvard has done is put three telescopes on the African continent. And he did this, interestingly, about 10 years ago. He was looking at what would really enable you to, if you look at the simulation, look at the timescales here, hours, minutes, seconds. This plasma is orbiting on very rapidly. And so in order to capture that in your reconstruction, you really need antennas, on as many as possible, on the African continent to achieve that. So I'll close out by moving away from our Milky Way, our beloved Milky Way black hole, into looking ahead and talking a little bit about gravitational waves as well. This is an image from the illustrious simulation where you really see, instead of things flying around, you see that cosmic structure. Galaxies are not randomly distributed in the universe. They tend to form along these filamentary-like structures, and where these filaments intersect, you have the most massive clusters. And the most massive black holes live in those most massive galaxies inside of those clusters. Now, you remember that I was talking about this cosmic time machine. By looking deeper and deeper, we see more distance. And you remember that this is the best model of our Milky Way, an average galaxy with a black hole at its center. If we now, in a supercomputer, play the rules of gravity forward, and we look at how that galaxy forms, how it comes to be, this is looking at Z of 11.9 there is, just think of it as soon after the Big Bang. And what we've done here is you basically have the initial conditions and you play the movie forward and you see what gravity does for you. And what you see here is the formation of that. It's a pity it's a bit laggy again, but you see the formation of a Milky Way-like halo. You were looking at dark matter here, but this is the merging of many dark matter halos to form one central halo in the center. Now, the way this evolves is that at some point there are supermassive black holes in a large enough dark matter halo. And if this merging process, you can see this little swarm and the formation of one of these large halos. And what's happening, this is just a small zoom in of one tiny region of the universe. This is happening for many, many halos in the universe. Well, it goes to follow that if there are black holes in those individual halos and those halos merge, there should be pairs of supermassive black holes at some point in the universe. So one of the things that, what we do with radio telescopes, and this is a survey that covers a very large patch of sky. There's the moon for scale now. Together with the South Pole Telescope, MeerKAT has surveyed 100 square degrees, and you see lots and lots of dots here. Each of these dots is one of those halos, hosting, on average, typically one supermassive black hole. But for some of them, you've got to look for the needle in the haystack. There are actually two that are in the process of either merging or inspiraling, and that actually turns out to be a very important enabling test of the evolution of physics. So what we're looking for are pairs of galaxies that are a little bit older than this. This is when they just get together. We want to look at them when they've kind of merged a little bit closer, which is what that movie was trying to show, a little bit jerkily. And at the heart of these two galaxies that are about to merge, they're in their first embrace. There's a supermassive black hole in the nucleus of that, and a supermassive black hole in the nucleus of that. Let's say of order a million times the mass of the sun. As those two galaxies merge, and here's another simulation, let's see how it works out. Here, we're playing gravity forward, and at the heart, you can't quite see it, but there are two white dots that represent the two supermassive black holes at the centers. They're jiggling around. That's actually real. That does actually happen. It's a bit accentuated here, just to illustrate the point, but still. They finally capture, and the black holes, you can see there, get together. They find each other, and they find each other quickly. They're in spiral, and that is a fantastic situation that is predicted to be the strongest generator of what we call gravitational waves. These are disturbances in space-time. They have a quadrupole nature, to as the physicists know. And as they get together, so this would be zooming in on the heart of those two white dots that we previously saw, they generate what we call gravitational waves that pervade the universe. That's one individual system, but remember, the cosmic tapestry, there are millions upon billions of these. So what that is doing is creating a disturbance in space-time that creates a quadrupole-like wave that'll make me shorter and fatter, taller and leaner in a systematic way. It's just a rapid change in the mass distribution, just in the way that electromagnetic radiation is a rapid change in charge. Gravitational waves are an accelerated mass. So you can also code this up. I don't think I did this in the sound, but you can actually look at this merging pair of black holes, and will it work? Alas, no. But if you can code this up, the actual changing of as the gravitational wave passes, the frequency increases as these spiral in, and so eventually it spikes, and we call that a characteristic chirp signal. Sorry, you can't hear that. Right, so that's fantastic. What do I do with it? It turns out that radio telescopes can actually sense the combined gravitational wave signal from all the supermassive black holes that are gyrating, orbiting around each other in the universe. That's quite a fantastical fact. But we use something that is akin to galactic GPS. So I'm going to have to introduce another very massive object here, but not quite as massive as ones I'm talking about. So it's a city-sized star called a neutron star, extremely dense. About 1 teaspoon would be all of humans' weight together. And they pick, astronomers pick a very specific type of neutron star. It's one that's spinning and has these lighthouse-like pulses, and it's called a pulsar. And the rotations of order of 50 million per day is what you require to use this. Reason you use that is to make it is so that it's the most accurate clock. It is one of the most accurate clocks one has, and we use this in this sort of galactic GPS way, because one of these spinning around 50 million times a day, you find several of them, and you model very accurately these lighthouse-like pulses that are appearing. And if you do that very accurately towards an array of these, you can sense any disturbances. It's a bit like if you were able to measure the distance to several buoys floating on the surface. You'd be able to sense changes. And this is what is done with pulsar astronomy, with pulsar chiming arrays. So the SKA at the center here would, in principle, if we were able to model, if it has the most accurate clocks at these locations, if there is a disturbance in the space-time, it would pick up characteristic signals, and these would correlate, these would be connected between these different pairs, and it would be able to detect gravitational waves passing through the Earth and the distant pulsar. So it's a lot to take in, I know, especially towards the end of the lecture, but really, I think this is one of the more beautiful experiments. In a nutshell, you're using a radio telescope on the Earth to observe the most accurate clocks in the universe, which are in your own galaxy. They're spinning neutron stars that are spinning about 1,000 times per second. Okay, you're doing that so that you can pick up the disturbances to space-time in the distant universe from two black holes that are around 1 billion times the mass of the sun, orbiting each other at separations about between us and the closest star. It's a lot to take in, but I really think it's one of the more beautiful experiments that has ever been conceived. And MeerKAT has detected gravitational waves using this. A whole range of telescopes have now, you would have seen last year, announced this discovery, but it turns out MeerKAT is doing this exceptionally well, despite being a relative newcomer to the experiment. And I think we're going to see some interesting things. Now, where this gets interesting is when you combine the SKA doing this beautiful gravitational wave experiment with the Event Horizon Telescope, which is actually giving you the sharpest view of looking for pairs of galaxies, well, pairs of black holes far, far further in than this, you actually are able to do both. In principle, if you could find the right black hole pair, you'd be able to track their orbits, despite them being billions of times the mass of the sun and being separated by of order. Well, I won't do that on the fly. You can actually do this experiment where you sense gravitational waves and make, movies effectively of these black hole pairs moving each other. Now, of course, you can't do them for all of them in the universe, but you can do it for a few examples in principle. And this is where the synergy of these two giant radio telescopes really comes together. There are also indirect signatures, and MeerKAT has made a beautiful image which appeared in the New York Times of one. This object previously, people were trying to figure out why does the supermassive black hole at the center here emit jets that are sort of egg-shaped. It wasn't clear. One exotic explanation was that there are actually two black holes at the center here that had recently merged, and that kicked the jet axis. It changed the orbital angular momentum in such a way that jets that used to travel this way suddenly had a rapid change to that. This beautiful MeerKAT imaging basically shows that's not the case for a whole bunch of reasons, but it actually shows that the young jets are in the same axis as the main, and it's actually got to do with the galaxy, why this plasma is bouncing off there, rather than some change in the angle. But a lot we have to do with not only looking at black holes in spiraling, but actually supermassive black holes merging. So it's an exciting future with these giant radio telescopes. The Square Kilometre Array, mid-frequency array, already existing as MeerKAT, will be expanded to MeerKAT Plus, and then eventually be SKA Mid. We'll be looking at both directly at black holes across cosmic time, and sensing these gravitational waves from those that are in very, very close orbit. So in summary, I think we really are in a golden age for radio astronomy and gravitational wave research. It's I think a partnership that we can really look at here in South Africa in building on these. This is extremely a whole range of opportunities in this domain. MeerKAT and EHT have already delivered some transformational results, and at the same time here in Africa, we're, while hosting some of these, only getting started as a community. There are lots of opportunities, as was discussed in the intro. Really, yeah, and this meeting testament to some of that. Yeah, and the future is bright. The youngsters, there are lots and lots of opportunities, limited only by your ambitions. So do get in touch, talk to people here at the conference and more broadly. Thanks very much.
Thanks, Roger, for that truly inspiring presentation. We have time for questions from the audience. I'll start with my colleague, Professor Ma.
Should I speak over the Okay, thank you. Thank you, Roger, for this nice talk. My question is, you talk about the merging of galaxies and so on, and by using this interesting synergy of MeerKAT and SPT. But if you see two galaxies, they are close, how can you know they are just about to approaching each other, or they have been through each other, like trying through each other once, and so on?
Yeah.
How do you know their
status?
Yeah.
You've actually just pointed out one of my master students' project with the Simba simulation. She's asking exactly that question. If you see pairs, it doesn't mean that they will definitely coalesce. And it doesn't mean that those black holes will find each other. And at the moment, our simulations with hydrodynamical simulations on cosmological scales do not really have the resolution to answer that question definitively, but they're getting there. So what she's doing is she's basically tracking the particle data of the Simba simulation and checking, do they actually merge within a given range? Yeah, that is not and working in partnership with Ramil Dave. That's not we don't know the answer to that for sure at this stage.
Thank you for a beautiful talk. You mentioned that the envisaged expansion of MeerKAT by adding more and more dishes to increase the number of baselines and to have a larger set of lengths of baselines, I suppose. How about making the baselines time dependent by making them mobile, by putting the whole business on a frozen lake or doing something more clever than that? How about that?
Yeah, so our US colleagues who built the very large array in New Mexico did exactly that. They had a Y shape. So you have three railway tracks, one going there, one going there, one going there. And every 3 months, they put the telescopes at 25-meter dishes. It's no mean feat. And they move it into a different configuration. And that allows you to do different science, because if you're sensitive to different spatial scales, you're able to do different science. It comes down to cost, but also if you have a large number of antennas, you can actually put them in we do what we call a log spiral, but you actually get pretty good imaging over quite a wide range of scales. So because we had 64 antennas to place, it was pretty reasonable. Now, an interesting idea, all of this is limited by the rotation of the Earth, right? So you're collecting up a number of Fourier components or notes limited by the rotation of the Earth, because as the Earth rotates, the projected baseline, the pair, slowly changes, and that samples a different part of the array plane. So the bright new idea, certainly in Event Horizon Telescope science, is to put spacecraft up and design very clever orbits that do not face that limitation of 24 hours, and you collect up your Fourier components far more rapidly and far more completely to make a more robust image.
Especially, when the first image of the Event Horizon Telescope producing the black hole image were made public, it was hailed as one of the yet another proof of the correctness of general relativity. And this being a Gravity Society meeting, maybe it might be interesting if you have any comment about whether this Event Horizon Telescope has any scope of constraint some of the modified theory models that you have probably seen and you might see in the next few days, people talking about modifications, exchanges of generality. Do you think either the result already produced or some upcoming tests of the Event Horizon Telescope can say anything about modifications?
Yeah, so I mean, in 2019, the first image was released. But I think even more extraordinary was 2022, when the Sagittarius A star results were released. You had two black holes testing and ring sizes predicted by general relativity, being able to compare that observationally with two black holes that range in mass by over 1,000, 3 orders of magnitude. And then on top of that, being able to compare that with general relativity tests that have been done with black hole mergers with the LIGO instrument. I think that in itself is pretty remarkable, but I think what you're going after is something more. Yeah. And I think, despite the fact that these images that have been released by the Image Horizon Telescope over the last few years, despite the fact that they are built on 4 decades of effort, huge contributions over many years by many people, that wasn't always as visible, wasn't always as, in the press, certainly. Despite the fact that that's been going for 4 decades, I think we're just getting started. I think this is remarkable validation within the uncertainties that you could see, but the contrast of the image, the brightest pixel to what you can actually make out is around about 10, between 10 and 50, depending on which image you deal with. It's not enough to do the highest precision tests of general relativity. We really need to add more antennas to turn this into a precision test. And I think we want to make those movies as well. So this has been a huge success off the back of 4 decades of effort that really, I would say, there is an amazing new chapter, and Africa has a key role to play there.
It's a question at the back.
Mine is a very, I wouldn't say it's a tricky, it's an easy question to answer or a difficult question to answer, but it's based on my own clarification. What is dark matter?
Sorry, I'm in black hole mode. So there's a lot of evidence that we have and have had for almost 100 years that there is mass there that we can't see through electromagnetic radiation. From the motion of galaxies in clusters, I mean, Fritz Zwicky noticed this back in the 1930s, did some back-of-the-envelope calculations, to the late 70s and the 80s, where astronomers in Europe and the US were measuring how matter rotates in galaxies and how it rotates. It seems to just go too fast in the outskirts of galaxies. So the inference there is that there's something that we're not seeing that's making that rotate too fast, or the galaxies move too fast in the galaxy cluster. We also see this with a phenomenon called gravitational lensing, which I indirectly introduced by looking at the shadow effect, where you see the photons bend around the black hole. By using lensing techniques completely independent of rotation curves, etc., we see strong evidence for more matter being there than we actually see. What it is the subject of a number of tests and experiments that are on the horizon. But it could be some new particle, it could be collisionless fluid, we don't know. But we have a whole lot of independent empirical evidence pointing to that being a key requirement in our cosmological model. And I think a lot of work, certainly by my colleagues at Wits, I think here at Stellenbosch as well, on the nature of dark matter. But I personally am no expert, so apologies.
Thanks, it was quite an illuminating talk. I just want to ask about how do you make the specific identification that you're dealing with a black hole? Because if you do, we've done some work and modeled wormholes, for instance. These are like probably fictional, but the picture comes out to be almost the same. The ring of fire photon sphere. Well, how do we know it couldn't be like a neutron star or gravitar star? Even that's speculative, but what is it that tells us specifically it is a black hole that we are seeing?
So you're talking about the EHT MH7 star image in particular?
Also the gravitational waves experiment, because even the Julie is out there, I think. Was it the coalescing of two black holes or two neutron stars? I think that question is still not settled, although it is believed it should be black holes.
Yeah. So yeah, this is definitely an area where I'm straying outside of my wheelhouse, but there have been a number of tests of hypothetical, if this is surface, if this is some reflecting surface, well, then it has to have far infrared radiation associated with that. And the constraints, the astrophysical constraints, when you combine X-ray, infrared constraints from what you expect thermally with the shape and shadow, it just doesn't match up. So yes, we want to improve the image. We want to continue to do this, but there are a range of constraints there. If you put in alternatives, you simply see different features. Now, I will admit there are some contrived situations where you could create this, but I think the repeated observations over multiple years, seeing this consistent, basically point to absolutely a black hole.
And they just add. So one of the evidence that we're against the wormhole scenario of the EHT, if you read the original paper, is to say if there's a wormhole, then that connect to another black hole, and if some matter falls in, then the matter will come some sort of going through the Einstein-Rosen bridges and come out of it. Therefore, you wouldn't see a dark image, a dark pixel in the center. That's as far as I understand. Yeah.
Thank you. Thank you for a lovely talk. Like my friend at the back, I'm also a bit concerned about dark matter. For me, dark matter is coffee without milk. But there's a lot we don't know about the topic, and it's one of the hot topics in physics. And I mean, there are certain assumptions we're making about the age of the universe, yet we don't know what most of the universe is comprised of. So I'm just wondering, what's the uncertainty around our understanding of the history of our cosmos based on what we currently know about, the topic of dark matter?
I think this is where precision cosmology has really made enormous strides over the last few decades. I mean, looking at the fluctuations in the cosmic microwave background really put incredibly tight constraints on, the baryon fraction, the dark matter fraction, these sorts of things. So that on its own. But then when you link that with independent experiments that have got nothing to do with early time cosmology, and you're getting consistent results, I think, yes, there is certainly room to improve the precision. But we've had there's been incredible success with this range of cosmological probes that have mapped the background to incredible accuracy and derive that. And then the ground-based stuff to do it at higher frequencies. So, yeah, I mean, what you're getting at is kind of missing physics and things rather than an uncertainty question. But I'm not sure it's in that. It's mine.
So, you mentioned even the current configuration of Event Horizon Telescope on Earth, then the only two black holes we can see are M87 and our own Sagittarius star. And because one is far, one is close, but because of mass difference, they happen to be on the same angular size. But then also you mentioned in the future, we might put some telescope in space, or maybe even moon orbit-based telescope. In that sense, you will open up a lot more configuration of the Event Horizon Telescope. And can we use those to see even further black holes and even smaller black holes?
Yes, so we're not 100% sure that Sagittarius star and M87 star are the only ones, but there's actually an active program to try and test if there are more that where it's possible to just resolve things. But I think the next step is really getting higher imaging fidelity and pushing to 345 gigahertz on the Earth. And then space is, on longer timescales, absolutely required to take this to the next level. And as soon as you push, I can't remember exactly the numbers, but as soon as you push to a few extra Earth diameter, you bring a whole range of black hole shadows into play, and you're able to start doing, statistics rather than looking at these two beloved nearby black holes. So I think, as you look into the 2030s and maybe early 2040s, there are going to be a range of fantastic, I really think they will fly, at least one of them. It's going to be interesting to see how that is done in concert with the ground-based stations, because there are a whole range of options there. But, 4 decades of effort, but you can look at the next few decades already and just how exciting and fundamental the science will be.
Question back.
I have a question based on your introduction of gravitational waves. So you mentioned that there are certain events that happened a few billion years ago, and these happened with quite some abundance, and that we can detect these events, like you mentioned, a merger. I would like to know how we can detect a signature of a black hole that does not have a characteristic chip. So, for example, how do we know our detection is not something like a primordial black hole? So what characteristic signature does something have that isn't a chip that we know for sure is a spiral, an in-spiral or merger?
Yeah. I mean, there are a whole range of chirp signals you can get just with different inclinations and different astrophysical effects if it's a complete vacuum between. I am definitely not an expert in that area. I think that's a huge parameter space that's obviously explored by the LIGO collaboration and others. Testing alternatives, I imagine it's fairly difficult to derive the parameters with the signal to noise that's in hand, especially for lower mass black holes. So testing alternatives, I imagine, would be tricky, but in principle possible. But I'm not familiar with the different models and can't comment intelligently on a good question.
Any other questions from the audience? We have questions from online as well. Ask the microphone for culture.
Hi, just a short technical question. I was just wondering, how do you synchronize the MeerKAT array with another array in South America or the South Pole? Because I'm assuming you need to be quite precise in your measurements.
Yeah, you need a very accurate clock to keep local time. So you need a maser on site, predictable pulses, not unlike the pulses that we monitor, pulsars. That we monitor with the MeerKAT radio telescope. But you need a common time axis, which you create with a special device called a maser. You have a maser at every single site, and then you're able to get that close enough that then you can calibrate. And you can look at what we call calibrator sources and make sure that we're basically correcting for any delays in the system to make it's typically a pinpoint of light towards a well-known source that we're able to link these up. So there is kind of a key piece of instrumentation that's required at every site, and then fine-tuning that happens in the calibration process.
And we could use something like a pulsar to do that calibration.
Not necessarily a pulsar. I was talking about pulses from a maser. So this is all going to get a little bit confusing, but you need a standard timing source that is saying this is the time now, and then you can make an increment on that, because that may not matter, because you need to account for things as extreme as tectonic loading due to the oceans, etc., which change the timing very, very slightly. If you turn this around, this is how you actually measure the rate at which the African continent is drifting in a certain direction at the sort of millimeter per year level. I think. Yeah.
Okay, there's a question online. What we got from NITheCS Public Lecture. Hi, Prof. Grateful. I have sort of a naive question. Galaxies merging, right? Do you guys have criteria as to how massive these galaxies should be? Because I'm assuming that it's mainly massive galaxies that have these SMB edges at their center. Or are you guys just using simulations mainly, no observations?
Yeah, it's a good question. I mean, it goes to, you know, what defines a galaxy versus just a cloud of some gas. Yes, we have to do this in a repeatable way. We have to actually define thresholds so that someone else can look at our analysis and redo it, either with that simulation or with a comparative simulation. But we have to define thresholds of both the stellar mass of the host galaxy, or the total mass of the host galaxy. We have to define thresholds of the relative mass of the black holes of the galaxy. And this is effectively slicing and dicing. But you're mostly interested in when very comparatively massive black holes pair up. That's what's going to generate the strongest gravitational waves. And that's what my students are focusing on at the moment.
Okay, I think we've had a really terrific bunch of questions after this really fantastic talk. So let's thank our speaker, Professor Roger Deane.